So when we want to expand a logarithmic expression, sometimes we're not very clear about what we mean. But what I should say is we're using the following rules. So we have the following, there's kind of three main rules for dealing with logarithms, which is that it can really be any base, kind of right, log base b. So log base b of a product is equal to log base b of a plus log base b of b. I feel like I can do this up. I want to see what I'm writing. Okay. And then if you have the log base b of a divided by b, it's the log base b of a minus the log base b of b. And thirdly, the log base b of a to some power is that power times the log base b of a. So those are your three main rules for either simplifying or condensing logarithms. So sometimes we go from left to right to kind of make our expression have many, many logarithms that are all very simple. Or sometimes we go the other way to combine everything into one logarithm, usually if you're like trying to solve an equation or something. So if I'm trying to make this a bunch of logarithms, well, I'm going to write it as, now I think you can do this you can probably do it in one step really. I'm going to do it in three. I would probably recommend two. So here's what I would say. I'm going to see that I have the natural log of something divided by something else. I'm going to write this as the natural log of the top stuff minus the natural log of the bottom stuff. And I probably should have done myself a favor and rewritten x squared plus sine of x in the square root as x squared plus sine of x raised to the 1/2 power. Probably would have been a good idea, but it didn't. So then I can break these up into more logarithms. I have a logarithm of a product. I can write this as the natural log of x cubed plus the natural log, instead of square root of x squared plus sine x, let's write x squared plus sine of x to the 1/2 power. Minus, now here's where you have to be a little extra careful. I have the natural log of, so if I just look at this without the minus sign for a second, natural log of x to the negative second plus 7 to the 4th times cosine x should give me natural log of x to the negative second plus 7 to the 4th plus the natural log of cosine of x. However, it is minus that. So it should be minus all of that, meaning the minus sign should distribute to each of those terms. So here's what I usually say when I'm expanding a logarithm of a complicated thing into many pieces. All the top factors, so my top factors in this fraction are x cubed and the square root of x plus sine x. All those top factors end up with positive coefficients, at least until I bring down any powers. I'm not done. I guess I'm going to take 4 steps to do it well. But all the bottom factors, x to the negative second plus 7 to the 4th and cosine of x, end up with negative coefficients. So personally, I am pretty comfortable with going straight from here down to there, saying, oh, it's the natural log of the top factor plus the natural log of the top factor minus the natural log of the bottom factor minus the natural log of the bottom factor. All the top factors end up having positive coefficients. All the bottom factors have negative coefficients. And then the last step is to bring down any powers. So this natural log of x cubed, I can rewrite. I should be using some equal signs here. These are all equal to each other. That 3 can come down and I can get 3 times the natural log of x. That 1/2 can come down and I get 1/2 times the natural log of x squared plus sine of x. That 4 can come down and I get minus 4 times the natural log of x to the negative second plus 7. And there is no power here, so I'm just going to write it as negative natural log of cosine of x. And that is the simplified, or I should say expanded into simpler logarithms version. Why would you want to do this? Well, taking the derivative of this last thing is much, much more straightforward than taking the derivative of this first thing. Let's do another example just to kind of have one more shot. And this will actually, we will frame in the following way. So I want to find the derivative f prime of x for f of x equal to the natural log of x, that's not an x to the 7th times the cube root of x squared plus 1 over sine of 2x times times the square root of x, just for fun. So hopefully you all agree with me that taking the derivative of that as is would be pretty awful, right? I'd have to do 1 over all that stuff, and then the derivative of all that stuff would be really, really terrible. I'd have to use the quotient rule, the product rule twice, and the chain rule at least a couple times as well. Right? It seems really, really terrible. So instead, we're gonna expand. And so here's my faster version of expanding. Here's my first step. I'm going to get the natural log of the top thing, so the natural log of each top factor. So f of x is equal to the natural log of x to the 7th plus the natural log of the cube root of x squared plus 1, also known as x squared plus 1 to the 1/3, minus the natural log of sine of 2x minus the natural log of the square root of x, or x to the 1/2. I think that's a perfectly reasonable first step. But if you want to take more first steps or more additional steps on the way to get there, that's totally okay. So now, the only other thing we want to do is bring down the powers. So I'm going to write, again, I'm still just writing my function. I haven't taken the derivative yet. I'm just simplifying. I've got f of x equal to 7 times the natural log of x plus 1/3 times the natural log of x squared plus 1 minus the natural log of sine of 2x minus 1/2 times the natural log of x. And now I've done as much simplifying as I can. Now I am at the point where I should start taking the derivative. So my derivative, f prime of x, 7 is going to hang out. So I get 7 times the derivative of the natural log of x, which is 1 over x. And I get 1/3 times, okay, it's been a couple days. The derivative of the natural log of some stuff is 1 over the stuff times. Yeah, I know. It's your favorite thing to say, the derivative of the stuff, right? That's always, right, chain rule, we're always multiplying by the derivative of the stuff. And then, ooh, here it's going to be interesting. The natural log of some stuff, the derivative is going to be 1 over that stuff. So 1 over sine of 2x times the derivative of sine of 2x. But the derivative of sine of 2x actually is the chain rule again. So the derivative of sine of some new stuff is cosine of that new stuff times the derivative of that new stuff. So it's going to be cosine of 2x times 2. And then we get minus 1/2 times the derivative of the natural log of x is 1 over x. And if you're web working it up, you can just type all this into web work. I would probably argue it's probably in your interest to simplify this just because it's easier to type into web work if you do actually simplify it. So I would probably write this as 7 over x plus 2x over 3 times the quantity x squared plus 1. This third part especially simplifies. Cosine of something over sine of the same something is just cotangent. So I could rewrite this as 2 times cotangent of 2x, which is much easier to type than cosine over sine. And finally, I get minus 1 over 2x. So I know it's kind of close to each other. So that's the probably easiest way to find the derivative of this particular expression. Yeah.
Why did you set it from?
So I'm using one of those log rules. So I could say for the same reason that the 1/3 here came in front, because whenever you have, so there's a rule that says if you have the that pen might have to go away. If you have the log, any base, doesn't matter what the base is, of x to some power, we can bring that power down in front.
Okay.
Now, there's actually a good reason for this. The reason is because of the other rule we have. So this is really just, this is just a version of this rule. That the log base b of a times b is the log base b of a plus the log base b. Oh, thank you so much. Appreciate it. Let's talk about that for just a second, because it is worth seeing. So you do need to be able to use these log rules that do come up. Here's why that is. So, okay, this is going to feel a little bit silly. So we all have to be comfortable with the fact that this is a rule. If you have the log base b of some product, it is equal to log of the first thing plus log of the second thing. And just to give you all a real example, let's write log base 2 of 4 times 8. Okay, I know it's not very exciting. 4 times 8 is 32. This is equal to log base 2 of 32. 2 to what power equals 32? The 5th power, yeah. Okay, on the other side, we could write this as log base 2 of 4 plus log base 2 of 8. Log base 2 of 4 is 2, because 2 squared is 4. And log base 2 of 8 is my favorite. It's what? Right, and 2 plus 3 is definitely 5. Check. So that rule really is true. There's one example of it. I mean, it doesn't prove the rule, but it does show that it's probably true. So now here's what I want to point out. If I take something like log base 3 of 7 squared, I could just use the power rule. But really what I'm doing is I'm saying, well, that's log base 3 of, I don't know what log base 3 of 7 is, right? It's not a nice number. It's 1 point something. It's not 2, because log base 3 of 9 is 2. Well, it's log base 3 of 7 times 7. And then I can use, sorry, I'm zoomed in. I forgot I'm zoomed in. Sorry. I'm going to be a little zoomed out there. 1 sec. Okay. I can use this rule and say, oh, log of a product is log of the first thing plus log of the second thing. So that's really log base 3 of 7 plus log base 3 of 7. But if I have something added to itself, I'm just doubling it. So that's really 2 times log base 3 of 7. That's why the power rule really works the way it works. And we could continue on, right? You could have log base 3 of 7 cubed and be like, oh, well, that's log base 3 of 7 times 7 times 7, which is really log base 3 of 7 plus log base 3 of 7 plus log base 3 of 7, which is indeed 3 times log base 3 of 7. So the power rule totally works. And you can even write, right, if you have log base b of x to some power, it's really log base b of x times x times x times x p times, which is really log base b of x plus log base b of x p times, which is p times log base b of x. Now I will mention, of course, this interpretation of it is only true if p is a nice positive integer, right? This kind of, this way of explaining it doesn't quite hold up if p is like 3.7. But we're just going to buy into the fact that, yes, this rule works no matter what kind of power you have, whether it's a nice positive integer or whether it's some fraction or some negative number, it's still going to work. Okay. Times. All right. So the other thing, yeah. So you guys, I was mentioning there is a small homework assignment that you have that's due tonight, I think, right? Due at 11:59 on today, right? That's, yeah. So there's not too much to it. It's kind of just using these rules of logarithms as well as some exponential rules. I feel like the only other thing that this homework assignment really gets at, well, I guess is going the other way, is condensing some logarithmic thing. So for example, I could ask, I want to solve following. Sure. 3 times the natural log of 2 plus, I'm making stuff up. It's not going to, this is not, I feel like I'm really, we'll see about this. Plus the natural log of x squared minus 7 equal to 4. This is probably going to be terrible. It might not even have a solution. It might, we'll see. So, natural log, it's a bad choice. It's a real bad choice. Let's make it natural log of 4 on the other side, just to make life a little bit more reasonable. So if I want to solve something like this, I kind of have to not rewrite it, but condense the logarithms into one logarithm. So that is a 3 times the natural log of 2. So I'm going to do a couple things. First, before you can put 2 logarithms together that are added or subtracted, you need the coefficients to be the same. Meaning we need them both to be 1. It's okay to have a -1, but we can't have a 3 here and a 1 there. So I really need this 3 to come up as the power. And we're going to get natural log of 2 cubed plus the natural log of x squared minus 7 equal to the natural log of 4. Ooh, let's do it this way. There's 2 ways you could do this. I'm going to do it maybe the more interesting way. I'm going to bring the natural log of 4 over to the left. So I really have the natural log of 8 plus the natural log of x squared minus 7 minus the natural log of 4 equal to 0. This adds a little bit of flavor to it. There's one kind of thing we'll see here that we won't see the other way. We'll do it the other way too, though. So now I'm going to condense this into one logarithm. These 2 pieces added together, we multiply the inside parts. So this part here becomes the natural log of 8 times x squared minus 7. Still minus the natural log of 4. 0. And then we can condense these 2 logarithms into one logarithm with a quotient. So this is going to be the natural log of the first stuff, 8 times x squared minus 7, divided by the second stuff. Now we can totally simplify that inside a little bit because 8 divided by 4 is just 2. So I can write this as the natural log of 2 times x squared minus 7 equal to 0. Now, if I actually wanted to solve this, I would need to rewrite it as an exponential equation. What's my base that I haven't written in this logarithmic expression? Everyone's favorite number, e. What's the power on e? You got 2 choices. Is it 0 or is it 2 times x squared minus 7? Oh, it's the other one. It's 0. Right? So it's always the base to this power equals that stuff. So e to the 0 equals 2 times x squared minus 7. And then we could solve this. It's not going to be very pretty. You'd have 1 equal to 2 times x squared minus 7. Then, yeah, it's probably, so I would maybe divide both sides by 2, I guess. Sure. This is not the fun part. So we get 1/2 equal to x squared minus 7. We add 7 to both sides. We get 7.5 equal to x squared. And then we take the square root of both sides, and we get x equal to plus or minus the square root of 7.5. Not my favorite number, but whatever. So I will point out, I kind of made this problem a tiny bit unnecessarily hard. But the reason I did it was to show that if you have like multiple logarithms on the same side, you can still combine them all together eventually. And I should point out, the things with positive signs end up in the numerator of the inside of the logarithm, and the things with negative signs end up in the denominator. It's not a coincidence. But the easier way to solve this, just so you all know, would have been to just say, if I go from here and just combine the things on the left, I can say that the natural log of 8 times x squared minus 7 is equal to the natural log of 4. And then if 2 natural logs are equal to each other, their insides have to equal each other. Right? There's no way that natural log of something equals natural log of a different something. They have to be the same somethings for them to equal each other. So we can just drop the natural logs essentially and say, oh, then we must conclude that 8 times x squared minus 7 equals 4. Which is really, then you're just back here, right? Then you divide both sides by 8, and so on and so on and so on. So that would have been an easier way to do it, but I wanted to make it a little harder just to show you how to combine all these algorithms. Okay. The only other thing this homework assignment I think is really asking you to know about is one more property of logarithms and exponentials, which is the following. The e to the natural log of some stuff is just that stuff. It's kind of a big deal. Comes up all the time. It's really true for any base, right? So it's true for e to the log base e of some stuff, but it's really true for also 2 to the log base 2 of some stuff is equal to that stuff. Or really any base to the log base b of to the log with that same base of your stuff. And I had written down some problems here. Yeah. So for example, they're asking you to solve something like, where did it go? And I wrote down some problems. Where'd they go? Oh, sure. Something like the following. For example, solving e to the natural log of 2x plus 5 equal to 1. It seems kind of annoying. So this one actually you can't, so, ooh, yeah. So this one I want to make sure. Yeah, this one I feel like they're trying to make you make a mistake. Maybe not. I don't know. I'm not, that's how I'm reading this. So I want to point out that e to the natural log of 2x plus 5, if we're not careful, we don't look at it carefully, you might think it's just 2x plus 5. But it's not, because I want to point out this is not the same as, so if I have this, which one is it? Is it e to the natural log of 2x plus 5 like that? Or is it e to the natural log of 2x plus 5? Good question. Well, if there aren't any parentheses written down, you kind of have to assume that once you've written like the first addition or subtraction sign after your stuff, that's it. So we have to stop right there. It's kind of annoying. So I would break this up. I would rewrite this as e to the natural log of 2x times e to the 5 is equal to 1. That's how I would go about solving this. And then e to the natural log of 2x is great. E to the natural log of 2x is just 2x. So 2x times e to the 5th equals 1. And then solving for x is not too terrible. We divide both sides by 2, and we divide both sides by e to the 5th. So we're end up getting 2x e to the 5th divided by 2 e to the 5th equals 1 divided by 2 e to the 5th. So we have x equal to 1 over 2 e to the 5th. So that's how what they're kind of asking you to do. They're really just asking you to use that one property that e to the natural log of some stuff is just stuff. Okay. I just wanted to address a few things on that particular homework assignment because I wanted you to know what they're asking you to do. Let's go ahead and let's go this way. So last class, we had done one example of a derivative where your base and your exponent both had variables in them. And there's definitely a few problems like that on not the homework assignment that's due today, but the one that's due on the 3rd, which is what, Monday? Yeah, okay. Oh, by the way, classes meet on Monday. This class does not meet on Monday because I will not be here. So we don't have class on Monday. It's canceled, but all your other classes still meet on Monday. So go to your regular classes, but I will not be having class because I will be flying on a plane. So I won't be here. We won't have class on Monday, but we'll have class on Wednesday. Okay. What else? Okay, so yeah. So let's say we want to find, and I'm going to write it in kind of the least convenient way possible. Find the derivative of 2x plus 7 to the x minus 3 power. And let me just double check one thing. Yeah, your homework assignment is nicer than this, which I appreciate. When they give you these problems, and very typically, when someone's giving you a problem where you have to find the derivative of something where your base and your exponent both have variables in them, usually they are kind and they say, well, really, we're going to find dy dx for y equal to 2x plus 7 to the x minus 3 power. And the reason it's important to actually write it as y equal to your function is because we have to take the natural log of both sides to be able to kind of deal with the situation. So that's what we're going to do first. We're going to take the natural log of both sides. So the natural log of y is equal to the natural log of 2x plus 7 to the x minus 3. The reason for doing that is to allow us to get that x minus 3 or whatever variable is in your exponent out of the exponent, right? We're using that logarithmic rule again. That's why we probably spent time talking about the logarithmic rule really is so that we remember, oh, we can do this thing because we do this thing a lot. We're going to bring that down in front and say, oh, I've really got the natural log of y equal to x minus 3 times the natural log of 2x plus 7. And now we're going to differentiate. I guess I could be writing like words over here. So take log of both sides, take natural log of both sides, I suppose is what I should write. And then bring down the power. Feels like a very like fight the power kind of statement. Bring down the power. Okay. And then next, we're going to differentiate both sides. And whenever you're differentiating the natural log of y or something with y, we're making the assumption, at least at this stage, well, it's not even an assumption here, right? We are making the very accurate observation that y is a function of x, right? Literally, right there, y equals some function of x. So when we differentiate natural log of y or natural log of some stuff, the derivative of the natural log of some stuff is 1 over the stuff times the derivative of the stuff. You're always thinking, oh, I'm thinking implicit, really. Thinking I need to remember that y is a function of x. And now the right-hand side, we have to use the product rule because we have two functions of x multiplied together. We have x minus 3 times the natural log of 2x plus 7. So the derivative of x minus 3 is going to be 1. I'm going to leave the other piece alone. If it helps, I think it does help. We can say, that like this is f, this is g, there's f prime, there's g, and then we're going to switch it up. And we're going to get f, which is x minus 3 times g prime. And g prime, so the derivative of the natural log of some stuff is 1 over the stuff times the derivative of that stuff. Wife is ordering some DoorDash. Yeah. All right. The next is just kind of cleaning everything up. So solve for y. Now, I think you can do this in one step. Oh, not solve for y. What do I want? What am I trying to find here? Right, I want to solve for dy dx. So I think this can be a one-step process, but sometimes people get caught up. So I'm going to write the end step and then I'll backfill the intermediate step. So I'm going to multiply both, I'm going to multiply both sides by y to isolate dy dx. And I'm also going to replace y with what it's actually equal to, which is 2x plus 7 to the x minus 3. So I'm going to get dy dx equal to, so I'm multiplying by y, but that's really that. So I'm getting 2x plus 7 to the x minus 3 times all of this, which I might simplify a little bit. I've got the natural log of 2x plus 7. And here I'm going to have 2 times x minus 3 on top over 2x plus 7 on the bottom. I'll just point out this is y. If you don't like skipping that intermediate step, that's totally fine. We can take the intermediate step of just saying, oh, I'm going to multiply by y, multiply both sides by y to get dy dx on the left equal to y times all this stuff on the right. And then the last step would be to replace the y with what it's actually equal to. I think you can do that in one step, but if you want to do it in two, totally fine. Questions, comments, observations? I'm going to do one more because there's one other kind of. There's another question on the like this on your homework that's a little bit different. It's a little bit weirder. It's similar. Okay. Process is always the same. So if you see base and exponent both having x's, you should think, oh, I'm going to have to take the natural log of both sides and to do these 4 or 5 steps. Natural log of both sides, bring down the power. In fact, why am I saying it? I think you also do one. So before we do another one, you are going to do one. I'll give you a not too terrible one to do. Why don't you try find the derivative? Let me give it to you the next way. Find dy dx for y equal to, let's see, what do I got here? Let's say we have 3x to the 7x minus 1 power. Give that a whirl. And so just follow the same steps. There's a little bit of a process, but it's definitely worth working through. I'll give you a couple minutes. Everyone at home is doing it right too. So I promised you another 30 seconds. Don't want to be a liar. Yeah, close enough. So very much the same process. We're going to take the natural log of both sides. So the natural log of y is the natural log of 3x to the 7x minus 1. And then we're going to bring down the power. So natural log of y equals parentheses 7x minus 1 times the natural log of 3x. I guess I should mention, although I'm not going to do it, technically you could expand the natural log of 3x as the natural log of 3 plus the natural log of x. I don't think there's a good reason to do that because you still have this multiplied by that, and I don't really want to like FOIL that out. It doesn't seem worthwhile, but you could differentiate both sides. So we get 1 over y times, you can either use dy dx or y prime. I like writing y prime just because it's less to write, but dy dx is totally fine. There's like something in my eye over here, sorry. Okay, anyway. And then product rule over here. So the derivative of 7x minus 1 is just 7 times the natural log of 3x plus leave the 7x minus 1 alone. And the derivative of the natural log of 3x is 1 over 3x times 3. And those 3's can and should cancel. Interesting fact, just so you're all aware, in general, if you take the derivative of the natural log of a constant times x, you always just get 1 over x. It's 1 over the constant times x times the constant, which is 1 over x. Which makes sense because you could also break up natural log of cx as the natural log of c plus the natural log of x. And the derivative of the natural log of a constant is 0, and the derivative of natural log of x is 1 over x. So it totally makes sense. It's just kind of funny. So then finally, we multiply both sides by y. So y prime equals y times 7 natural log of 3x plus 7x minus 1 over x. And then finally, we replace y with what it's actually equal to. Or you could have done that in one step and gotten y prime equal to 3x to the 7x minus 1 times 7 natural log of 3x plus 7x minus 1 over x. Okay. So it's the same thing over and over again. It does take practice to like make sure you're not missing things. It's really kind of, I would say probably the most dangerous part of this is the part where you're taking the derivative of both sides, because it's kind of easy to mess up the product rule somehow. Let's look at one more example, just because there is kind of one other flavor of this on your homework, which I feel like is extra complicated. So let's go ahead and move this over here. So let's say we had the following spiciness. Let's say we had y equal to 2 to the x to the 8 to the x minus 1, which looks really like just a lot of garbage. I am not a fan. But the process is still the same. It's just extra terrible. Well, I should say the process is the same, but it's going to be in our interest to maybe do more simplifying than maybe you usually would. So check this out. We're going to take the natural log of both sides. So we got the natural log of 2 to the x to the 8 to the x minus 1. And even though it's not written that way, yeah, you should be aware that exponents are kind of funky. So 8 to the x minus 1 is kind of in its own parentheses. We didn't write it, it's not written in the problem, but it is. So I guess what I'm trying to get at, and let's just take a quick journey over here, because I want to point something out. If someone writes 3 to the third to the third, what does that mean? Is that 3 to the 27th power? Or is it 9 to the third power? Or is it 27 to the third power? So here's the thing, and this is kind of terrible. If it's written that way, you have to kind of assume that you're working from the uppermost exponent first. So without any parentheses, this has to be 3 to the third. And 3 to the third is 27. So that is 3 to the 27th, which is big. Right? I don't know, that's a giant number. On the other hand, if someone writes this, 3 to the third, that's a totally different animal. That's, well, now I'm doing the, well, first of all, you could actually do either 3 to the third first and get 27 to the third, which is not too terrible. It's 27 times 27 times 27. It's not that big a number. It's certainly a lot less big than 3 times 3 times, right? That's super right. Or you could say, well, really, if you have a power to a power, what can you do with those powers? So really, I can say this is 3 to the 3 times 3, which is 3 to the 9th, which is definitely not 3 to the 27th. So I just want to point out that when this is written this way, you can't say that you have like a power to a power and multiply the powers. This is definitely not 3 to the 9th. It's 3 to the 27th. It comes up sometimes, but it seemed like an opportune place to mention it, so I'm mentioning it. Okay, so you couldn't, for example, say here that this is 2 to the x times 8 to the x minus 1. Or maybe you could, but I don't want to take that chance. I definitely, like, there's just too many powers involved here. So now we're going to bring down the power. So I'm going to get that the natural log of y equals 8 to the x minus 1 times the natural log of 2 to the x. But then you might say, well, James, there's still more powers I can bring down. I can still bring down the x, all right? There's no reason I can't. So I could actually write this as the natural log of y equal to 8 to the x minus 1 times x times the natural log of 2. Now, fortunately, we still only have to use a regular product rule when we differentiate this, because I only have two variable things multiplied together. I could think of this as my f, and this other part here is my g. because x times natural log of 2 is just x times a constant. Natural log of 2 is like 0.7-ish. I think it's like 0.69, but whatever. So now we're at the place where we're going to differentiate both sides. But I do recommend, right? I do think bringing this x down as well makes it easier to take the derivative of this. Taking the derivative of the natural log of this, although it would be totally fine, it's going to be simpler, I think, if you do that. But either way, it's fine. So taking the derivative of this, we get 1 over y times y prime. And then taking the derivative of this, oh, what's the derivative of 8 to the x minus 1? I know we talked about it like a couple classes ago. When your base is an e, well, let's remind ourselves. What's the derivative of e to the x? Right. What's the derivative of e to the stuff?
E to the stuff times the derivative.
Yeah, that's what we like. Okay, so the only difference between e and a different base is that if your base is something else, if you have like, say, a to the stuff, your derivative is a to the stuff times the derivative of the stuff. And what other thing do we have to throw in there as well?
The natural log.
Awesome. Yeah, the natural log of your base. Technically, if you wanted to, you could say, well, it's in the first one as well, right? I'm also multiplying by the natural log of my base there. It's just that the natural log of e is 1, so we don't write it down. So really, you're always multiplying by the natural log of your base. It's just that when your base is the natural base e, it doesn't change anything. So the derivative of 8 to the x minus 1 is 8 to the x minus 1 times the derivative of my stuff is just 1, so I'm not going to write it down, times the natural log of 8. That's my f prime. And then I'm going to multiply by g, so x times natural log of 2. Plus, switch it up. I'm going to have 8 to the x minus 1. That's left alone. That's my f. And then times my g prime. So the derivative of x times a constant, and when everybody's super clear about this, derivative of x times a constant is just the constant. The derivative of x times 7 is just 7. The derivative of x times 0.69 forever and ever and ever, whatever the numbers are, is just 0.69, whatever the numbers are, right? It's just that constant natural log of 2. Or if you prefer, just in case you had done it the other way, I will just tell you all that if you had left it as the natural log of 2 to the x, the derivative of the natural log of 2 to the x is 1 over the stuff times the derivative of the stuff, and the derivative of 2 to the x is 2 to the x times the natural log of 2, and the 2 to the x's cancel out, and you get natural log of 2, same way. Oh, kind of cool. Not every, sorry, I forget. I don't have all the magical powers I want here. It's all right. Okay, so let's do the simplification in one step, or I should say the winding up. So y prime is going to equal y, but y is just 2 to the x to the 8 to the x minus 1 times all of this. 8 to the x minus 1 times natural log of 8 times x times natural log of 2 plus 8 to the x minus 1 times natural log of 2. And if you really wanted to simplify this more, you could totally factor out from inside this brackets an 8 to the x minus 1 and a natural log of 2. I don't think that's necessary, but you might want to. Okay. I'll see if I can get the way here. So yeah. So the next homework assignment that you all have due on Monday night is a lot of just taking derivatives of logarithmic things and exponential things, which we've kind of talked about a lot already. So just to throw one more example at you that's not this, let's say we wanted to find the derivative of the following, not that either. We would like to find, say, what do I got here? Let's make it interesting. Let's say we want to find the derivative of, oh yeah, we'll do that. Let's say we want to do like x squared times log base 4 of x cubed minus 17. I want to find that derivative. So I definitely see a product rule, right? I have x squared times a logarithm. And I should also observe, I can't simplify that logarithm, right? It's not logarithm of a product or a quotient, or there's not a power I can bring down. I can't bring that 3 down because it's not the power on the entire thing in the logarithm. So I'm stuck with it as is. I should also be aware of the fact that I have a log base 4, not a natural log. So just like in the previous problem, or similar to the previous problem, when our base was 8, we ended up multiplying by the natural log of 8. Here, since we have a logarithm with another base, we're going to end up dividing by the natural log of that base. And we take the derivative of that. So let's see what we get here. So derivative of the first part is going to be 2x. Leave the other part alone. That's the easy part. And then we're going to switch it up. We're going to have x squared times the derivative of log base 4 of some stuff. So that's going to be 1 over the stuff times the derivative of the stuff, which is 3x squared. And then we also need to divide by a natural log of 4. I usually just like to write at the end times 1 over natural log of 4. Some people would like to prefer, some people would prefer I write it like this. We could write this as x squared times 3x squared is 3x to the 4th on top, divided by x cubed minus 17 in parentheses, and then the natural log of 4. That's a more compact way of writing it. So yeah, when your base is something other than e in a logarithm and taking the derivative, you end up dividing by the natural log of that base. Whereas if your base is something other than e in an exponential state function, you end up multiplying by the natural log of that base. That's kind of the thing I've observed. I've always observed. Like, oh yeah, exponentials, you end up multiplying by the natural log of the base. If it's not e, logarithms, you end up dividing by the natural log of the base if it's not e. All right.